Welcome to a lesson with Dr. Powell. Let's take a look at the last practice problem that we had, where we were finding the instantaneous rate of change at x equals 1 of this function. So we already worked through this, but the way we did it is we used what I'd call the A strategy. So basically we had this curve, we had a point where we were heading toward to find the instantaneous rate of change, the slope of the tangent line of that point. So this point was a 1. We plug 1 into the function to get out 2. And the other point was we had a, and then we plugged a in, we get a plus 3. And what we did is we found the rise over the run. So this minus that, a minus 1, a minus 1. So this is rise over run, an average rate of change. And then we were taking a limit of this as the a value approached the 1. As the point moves to there, the a is going to approach 1. So this right here is what you'd call a difference quotient. It's an average rate of change. Oh, wait a minute. Why is it called difference quotient? What's a quotient? A quotient is a fraction. And difference, we'll see differences because, difference between two different things on top and bottom. This is rise over run. Okay, this is one way of forming a difference quotient that we can take a limit of. In this particular case, it's the limit as a approaches 1. But we're going to look at another strategy, I'll call the H strategy. Where h is going to be a variable representing the run. Okay, so on our curve, then we can think we have a point 1, 2, and then this point, maybe I'll make it a little further away so you can kind of see. All right, so our run we're going to call h. So if our run is h, then what's our point right here? What's the x value of that point? Well, 1 plus h, right? Because we've gone h over from 1. And then what's the y value? Well, we've got to stick that 1 plus h into the function, into the x spot right there. So 1 plus h will come in for x there. And then we'd get the square root of, you throw the 1 plus h in, 1 plus h plus 3. Okay, so then average rate of change, fraction that represents this average rate of change, the rise over the run, we can call a difference quotient. It'll be a different difference quotient than this one. However, the limit that we get will be the same. And we're going to take a limit as the run goes to 0 because we want these 2 points closing into each other, these 2 points closing into each other. In this case, this means that the run is going to 0, which is equivalent to the idea of a going to 1. Okay, h going to 0, a going to 1. Great. And then if you saw in the last video, it talked about how if you swap the order, it doesn't matter which side you're working on, same thing here. So really this is a limit as h is approaching 0 from either side. So if h is a positive distance or a negative one, it'll work both ways. So rise would be just simply the y values subtracted each other. So, and I can rewrite this as actually h plus 4. So this y value minus that y value all over this x value minus that x value, which actually is just h, because you think about it, 1 plus h minus 1 is just the ones cancel, just give you h, but that should be expected because h is actually equal to the run. We decided h would be the thing that would be in the denominator itself. So this would be what we have, and we're taking a limit as the run itself, h is approaching 0. So we have, this is another example, a different example of a difference quotient. So we have this difference quotient and we have this difference quotient. In the last video, we ran through and saw that this limit was equal to a fourth. This is also, the limit will also be equal to a fourth. And we can make the computation in a similar way. So we think, okay, if we multiply, well, first of all, we can't plug in h is equal to 0 because it's undefined. But maybe we could get, the top is actually equal to 0 as well when we plug in h is 0. So if we could get an equivalent fraction with the numerator, looks simpler, maybe we can get some kind of cancellation with that h in the denominator and have a domain change so we can plug in 0. That's kind of the idea. So if we were to take the top, multiply it by something, in a difference of two squares type fashion, so that, this would become the first thing squared minus the second thing squared, which happens with the minus and a plus here like this, which is nice way to eliminate square roots, and at least on, one part of a fraction. We have h, and then we have square root of h plus 4 plus 2. So and we're taking and that's going to be equal to the limit of this as h approaches 0. Notice on the top we're going to get h plus 4 and then minus 4, because it's this thing squared minus that thing squared. And then and that's okay, and then the bottom we have an h square root of h plus 4 plus 2, and make sure to put your limit symbol in there as well so you know what you're doing. Now notice in the top that cancels, so the whole top is just h. So h is actually now a factor of the top. And so you see the h and h, since h is a factor of the top, because it is the top, and h is a factor of the bottom, you can divide top and bottom by h and it will cancel out. You'll be left with a factor of 1 on the top. So really, this looks like the limit as h approaches 0 of 1 on the top, and then square root of h plus 4, that's 4, plus 2. And at this step, you can actually plug in, maybe I'll make that a little bit more clear. Okay, let's just rewrite that a little bit better. So we got h plus 4, and then when we plug in h plus 4, then we can plug in 0 for h, and notice we'll end up getting 1 over square root of 4 plus 2. Hey, that's 1 over 2 plus 2. That's a fourth, just like we wanted, right, from before. So this limit is also equal to 1/4 as desired. Okay, so that was a little video description of the same one as the last problem, just using an H strategy instead of an A strategy, and kind of describing what the difference of them is. Okay, thanks for watching.